What we want to do now is draw the Lewis structure for ions. The first ion will be a cation. It's the ammonium ion, which you should be familiar with. It's nitrogen with 4 bonds to it, and every time that nitrogen has 4 bonds to it, it has a positive charge. So we start the Lewis structure in the same way we do all Lewis structures. We count the total number of valence electrons in the chemical species. Nitrogen in the periodic table is in group 5, so it has 5 valence electrons. Hydrogen is up here in group 1, so it has 1 valence electron, but there are 4 of them, so that's 4 times 1. And then we notice that we've got a plus charge on this cation. Well, you know what happens when an ion forms that's a cation? Electrons are given up. So what we have to do is subtract the number of electrons designated by the charge. Since this is a +1, we subtract 1 electron. So that gives us a total number of valence electrons of 5 plus 4, that's 9, minus 1, or 8 valence electrons for the ammonium ion. Okay? So now we're going to draw our structure. Our central atom can never be hydrogen. It's got to be nitrogen in this case. So we go ahead and put our central atom, and then we populate around our central atom with hydrogens. And once we get our 4 hydrogens, we give every element what it wants in terms of electrons. Hydrogen, each hydrogen wants 2 electrons, and nitrogen wants 8 electrons. So 2 for hydrogen and 8 for nitrogen. Count them all up, 2, 4, 6, 8. If I have 8 valence electrons and I use 8 valence electrons, that means I have none left over. That means my structure is complete, with the exception that since it's an ion, the convention is to go ahead and put brackets around our ion and a +1 charge outside the brackets. So now we know our structure is complete. This is the Lewis dot structure for ammonium ion. Let's try another one. Let's try an anion in this time. Let's try cyanide. Cyanide, Cn with a -1 charge. So we're going to go ahead and let's go ahead and get this started. Count the number of valence electrons in the cyanide ion. If we look at carbon, carbon is in group 4, so it has 4 valence electrons. Nitrogen again is in group 5. It has 5 valence electrons. Now, since there's a -1 charge, as with all anions, that means we've added an extra electron. So if it's a -1, we add 1. If it were a -2, we would add 2. Let's go ahead and add up all the electrons we have. 4 plus 5 is 9, plus 1 is 10 valence electrons. All right, so there is no central atom. There's simply carbon and nitrogen. Let's give everybody what they want, and what everybody wants is 8 valence electrons. We'll put a pair here, a pair up here. So nitrogen's got 8. They're sharing 1 pair of electrons. That's what's making the bond. And then we complete the octet for carbon. 2, 4, 6, 8. Carbon's got 8. And 2, 4, 6, 8. Nitrogen's got 8. Let's count up the total. 2, 4, 6, 8, 10, 12, 14. Oh my gosh, I've used in this structure that I've drawn 14 electrons, but I only have 10 electrons. That means I'm 4 electrons over what actually exists in the molecule, or sorry, the ion cyanide. So what I have to do is I have to make multiple bonds. So here's how you make a multiple bond. You remove 2 non-bonding electrons from each atom that are involved in the bonding process. So we're removing a pair from nitrogen and a pair from carbon. Now, don't worry about that because we're not taking away electrons that actually exist. We know that they don't exist because cyanide only has 10 valence electrons. So we're removing 4, but we're going to replace the 4 with 2 valence electrons between the carbon and the nitrogen. So we've now added 2 more bonding electrons, but we've still got 2, 4, 6, 8, 10, 12. We're still 2 over. We need to make a total of 2 extra bonds, not just 1. So we're going to do this again. We're going to take 2 more electrons from nitrogen, 2 more electrons from carbon, and we're going to replace 4 electrons with 2 in between the nitrogen and the carbon. So now we have 2, 4, 6, 8, 10. Each atom has 8 electrons, 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for nitrogen. We've got a total of 10 electrons. Our structure is done. Now that's not very pretty, so we're going to clean it up a little bit. We're going to go ahead and instead of using dots for the bonding electrons, we'll go ahead and we'll use lines. Each line represents 2 electrons, and then we'll put a non-bonding pair of electrons on nitrogen and a non-bonding pair of electrons on carbon. Still not very pretty, but folks, best I can do under the circumstances. We'll go ahead and put brackets around it, indicating that it is an ion with a -1 charge, and that is our cyanide ion. All right, let's do one more before we call it a day. Let's take care of carbon dioxide. Now, carbon dioxide is a molecule, it's not an ion, but we're going to go ahead and find out a couple of things about carbon dioxide. So first things first, let's go ahead and count up the number of valence electrons. Carbon is in group 4. That means it's got 4 valence electrons. Oxygen is in group 6. That means it's got 6 valence electrons, but there's 2 oxygens, so we need to multiply that times 2 and then add them up. So 2 times 6 is 12, plus 4, that's 16 valence electrons for carbon dioxide. Carbon's going to be our central atom, so we'll go ahead, put carbon out here. We're going to do what seems logical, and that is to put oxygens on either side of the carbon. Just seems right to do it that way. Now let's give everybody what they want. Oxygen would like 8 valence electrons. So we'll give oxygen its 8 valence electron. Carbon wants 8 valence electrons, including those 2, and then 2 more. It'll share a pair here with this oxygen, and then a pair of non-bonding electrons down here. And then let's complete the octet for oxygen. We'll count up all of the valence electrons for oxygen and for carbon dioxide. Here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. My gosh, I've used 20 electrons to draw this structure, but I only have 16 valence electrons. In other words, carbon dioxide doesn't have 20 electrons. It only has 16. I'm 4 over. So what I have to do is modify my structure. And if I'm 4 over, it takes 2 electrons to make a bond. I'm 4 over, so I need to make 2 additional bonds. All right, so I'm going to do what seems logical under the circumstances. I'm going to go ahead, let me move this a little bit so I get a little bit more room to draw. I'm going to go ahead and redraw the structure, but first I'm going to make a double bond by taking a pair of electrons from carbon, a pair of electrons from oxygen on this side, and I'm going to replace it with 2 electrons in between the oxygen and the carbon. I'm going to do the same thing between this oxygen and carbon. I'm going to take the non-bonding pair of electrons that's on this carbon, and I'm going to take a non-bonding pair of electrons that's on this oxygen. I'm going to remove them and replace them with 2 bonding electrons. So I've removed 4 electrons, replaced them with 2. Let's see if our count is right this time. I've got 2, 4, 6, 8, 10, 12, 14, 16. So that is right. I've got 16 valence electrons. I use 16 valence electrons, and my structure is done. However, let's go ahead and let's redraw the structure with lines to make it a little bit easier to see what we're about to talk about. So we'll go ahead and do the best we can, make this as neat as we possibly can. All right, so there's our structure. 2, 4, 6, 8, 10, 12, 14, 16. We're looking good. Here's our carbon dioxide molecule. Now, the truth of the matter is, I could have elected to draw my carbon dioxide molecule obeying all the rules of Lewis structures, and I could have wound up with this structure. And this structure still obeys the octet rule. It has 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16 electrons. So which structure is the more reasonable structure? Which is the structure that we would be most likely to determine or to discover carbon dioxide to actually be in? Well, we determine which structure is the most reasonable by using a device called calculating the formal charge on each atom in the molecule. And it's an easy calculation, but you have to remember it. Formal charge is calculated by taking the number of valence electrons that an atom has. So for instance, oxygen has 6 valence electrons. And what we do is we subtract from those 6 valence electrons all the non-bonding electrons that are attached to that oxygen. So it's all the non-bonding electrons, and I'll just call that NB electrons, plus 1/2 of the bonding electrons. I'll just call that bonding electrons. So we take the sum of all the non-bonding electrons on a particular atom in the structure plus 1/2 of the bonding electrons. So in other words, if we're looking at carbon dioxide here, this oxygen has 4 non-bonding electrons, and it's got 4 bonding electrons that it shares with the carbon. And so this oxygen will get 1/2 of those bonding electrons. So in our calculation of the formal charge of this oxygen, we've got 6 minus all the non-bonding electrons, which is 4, plus 1/2 of 2, 4, 1/2 of 4, and 1/2 of 4 is 2. So that's going to be 4 plus 2 is 6. 6 minus 6 is 0. And we always put the formal charge just to the upper right superscript on the atom. So this oxygen has a 0 formal charge. If we go over to this oxygen, it has exactly the same structure as this oxygen, so its formal charge will also be 0. For the carbon in this case has 4 valence electrons. It has no non-bonding electrons, so that's 0 plus 1/2 of the bonding electrons. If we look at the bonding electrons, 2, 4, 6, 8 bonding electrons, so that's going to be 1/2 of 8, which is 4. That's 4 minus 4 is 0. So the formal charge on this carbon is 4. So we have a 0 formal charge on all the atoms in the molecule. Now that's what is desirable. It's desirable to have a 0 formal charge on all the atoms in a molecule, to keep the formal charge on each atom as low as possible. Let's take a look at this structure and see why it's not the most reasonable. If we look at carbon, Carbon still has 4 valence electrons. It has 0 non-bonding electrons plus 1/2 of the bonding electrons, and it has 8 bonding electrons. 2, 4, 6, 8, and that's 4 minus 4, which is 0. So the formal charge on carbon here is 0. For this oxygen, if we're going to do the calculation, oxygen has 6 valence electrons. It has 2 non-bonding electrons, so that's going to be 2 plus 1/2 of the bonding electrons. How many does it have? 2, 4, 6 bonding electrons. 1/2 of 6 is 3. So that's going to be 2 plus 3. So 2 plus 3 is 5. 6 minus 5 is a plus 1. So this oxygen has a plus 1 formal charge. And generally speaking, we just put a plus sign there, indicating that it's a plus 1. If it's a plus 2, we'll put a plus 2. Let's take a look at this oxygen over here. Calculate the formal charge of this oxygen. 6 valence electrons minus 2, 4, 6 non-bonding electrons. It gets all of those, and 1/2 of the bonding electrons. There are 2 bonding electrons, so we take 1/2 of the 2, which is 1, and 1 plus 6 is 7. 6 minus 7 is minus 1. So we'll put a little minus sign in up there to the upper right superscript, indicating that this has a minus 1 formal charge. So what's the purpose of this? Well, because the formal charges aren't 0 on every atom, this is inherently less stable and so not as reasonable as the original structure that we drew. But if you have to assign a negative formal charge to an atom in a molecule, it's best to put it on the most electronegative atom that's in that molecule. So this oxygen really doesn't mind the minus sign because oxygen is very electronegative, something that we're going to take another look at in this chapter. On the other hand, oxygen over here on the right-hand side has a plus 1 formal charge, which it doesn't like at all. Oxygen's electronegative. It likes to have electrons, so when it has a plus 1 formal charge, it's not a very happy camper, and this structure is not a very reasonable structure. It's not saying that the structure doesn't exist from time to time, but this structure is a much more reasonable structure. It's a structure with lower formal charges on all the atoms, and it's the most stable structure.